Awesome. Welcome to the first episode of WTF is FFI. My name is Andy, and here we have a very special guest. Here's actually my co-host, Aapo, a software engineer and purveyor of the dark arts of foreign function interface. That's right. Say that 3 times fast.
That's
Today,
hard.
that's hard. So today we're going to be going over intros to FFI, and Apple will be doing some live coding and some demoing for us. Apple, what should we expect from this interview, from this first episode?
Very like basic stuff. So as you said, we're gonna answer the question of WTF is FFI. So if you already know FFI, this is not gonna surprise you. Most of it anyway. We'll just kind of look at what's FFI, what foreign function interface is, how does it work with Deno, and why you might be doing it.
Awesome. And yeah, why don't we just get started? So my experience is very limited with FFI, and I think that this is going to be much of a learning process for me too. What is FFI, and why does it even exist? Let's start there.
Yeah, FFI, as the acronym says, or acronym goes, is foreign function interface, which refers to essentially programming between let's try that again.
Yeah, go for it.
So programming between two languages, bouncing between your language and then some other foreign language. So that's where the foreign part comes in, and then of course, interfacing with that other language, usually through functions. And why would you do foreign function interfaces, or why would you do FFI coding? Is basically there's a lot of great tools out there in the world. A lot of them written in some language that you might not know or you might not want to program in, but they will probably offer or might offer an interface that can be used for them a foreign language. So maybe you're programming in Rust and you want to use some library that is programmed in C++. You just use the foreign function interface to interface between your code and their code. And in Deno, we then offer the same API. We have our own FFI API that can be equally used to interface between Deno and, say, C++ or Rust or whatever.
Love that. Only the most perverse engineers would find this, will seek out this sort of this need. So I applaud you for that. And before we dive in, I'm just curious, why Deno in particular?
For me, it really boils down to first, of course, I'm a TypeScript, JavaScript programmer by trade, but it's somehow exhilarating. It's wonderful combining two worlds that never should they meet into one complete package. So JavaScript, usually you don't see raw bytes, whereas foreign function interfaces generally are, you would often write them with a C API, and it's all about raw bytes. And having those two in the same language, in the same kind of runtime, it really makes my fingers tingle. It's lovely. I'm absolutely in love with the whole thing.
I love that. And before we dive in, let's tell the viewers a little bit about you. Like, what do you do for work, and how did you find Deno?
Yeah, I work as a software engineer or software architect at a large company in Finland, and my day-to-day work is writing TypeScript, actually front-end TypeScript programming, and then a little bit of back-end side. I I guess I must have heard about Deno through Reddit and somehow found it very interesting. And around the time when the original since scrapped Deno plugin system was being replaced with Deno FFI, I started thinking, yeah, I really want to try this at work. And I started trying out how the new Deno FFI works and how it could be used at our company. And I've been then ever since using Deno FFI and especially contributing to the Deno FFI development in Deno itself.
Yes, that's great. That's great. And not only that, you also have a wonderful resource online. What is that again? I always forget the name.
Denonomicon. It's a callback to the Rustonomicon, which is Rust's kind of deep dive into how Rust works and what parts of Rust are safe, what are unsafe, and so on.
I love that.
So I host the Denonomicon, or I write the Denonomicon, which is hosted on Deno Deploy. There I try to, in mostly kind of down to earth, understandable language, try to write and explain how Deno FFI works. What are the kind of intricacies that you need to think about when you're writing foreign function code in general, but also in particular with Deno, because writing between JavaScript and C APIs or C++ APIs, there are things that you might not kind of expect from usual FFI programming.
Mm-hmm. Got it. Yeah, we'll drop a link to that in the comments. But yeah, let's keep the tingling feeling in your fingers going. Should we start with the main section of today's episode?
Yeah, let's start doing a little bit of FFI programming. So I've kind of prepared. I'll not lie to you. I will not be purely coding from memory, but I have here a small FFI library written in C++, and the beginnings of a binding library written in Deno for it. So let's first kind of take a very, very quick look at the C++ side. If you've done C++ coding, then this is bread and butter to you. If you haven't, it's nothing too earth-shattering. We have some namespace here, and in it we have a class which has some methods and some private data. And then we expose a C API for this library that essentially we have some static functions here, adding U32s, turning doubles to bits, and so forth. And then we have some APIs that expose the class to us through a C API. So an API to create, an API to delete, and then some method APIs.
Got it. Yeah, I haven't done C since high school, so this is haven't looked at this sort of stuff in a long time. But so the main function here really is add U32 and a few coercion functions, right?
Yeah, we'll start with the add 32. So kind of as a very, very basic step into foreign function interfaces, we have an API that returns a uint32 and takes two uint32s. In Deno, how we open this library that we've built, we have the Deno DL open function here. It takes a definition yeah, let's not look at that. That's not really working well. So it takes a file name and then a definition for the library. Here we're getting the file name through a new URL, and we're just calling the new URL with our libsession1.so. So that's the file name of our already built dynamic library, and then import meta URL, so our kind of local file name here. But then we have the symbols definition. And here we've already defined the first function that we saw, the add u32. We need to define its parameters and its result type. The parameters, we saw that it took two u32s or uint32t's in C++. So we define here as well that we take two u32s, and the result is, or the return value is likewise a u32. Now,
so just to clarify, the object parameters and results, is that like a required thing that is for typing for Deno, or is that, like, what is the purpose of that?
Yeah, so the parameters and result are required. A C API or a foreign function interface, native language functions will always require kind of proper typing in some form or another. With the parameters and results here, we're essentially telling Deno that when you open this, or when you load this libsession1.so, you will find there this add u32 symbol. And we tell you that it is a function which takes two u32 parameters and returns a u32. If we say here that the parameters are a u64, an i8, and a pointer, Deno will believe us. And Deno cannot actually check if we've lied to it, if we've made a mistake. There is no way to for Deno to automatically know if we have the parameters and the result type correctly or not. The only thing it can actually check is the name. Does add u32 really exist in this library or not? And beyond that, the types, parameters and result types are kind of on us to have correct. They're used when the function is actually called, and they will also give us type information, type feedback. So since we have defined the add u32 in the symbols, the resulting lib will actually have the symbols object, and in it we can already see that there is an add u32 function there, which takes two numbers and returns a number, because all u32s are valid numbers, and yeah, not vice versa, but yeah.
Got it. That's good to know. Yeah.
And now, if we actually try and use this function, we can, let's console log this. So we can console log calling the add u32 with two parameters. Of course, since this is TypeScript, it will it won't warn us about wrong parameters. No, yeah. So it will, because this is TypeScript, it will actually warn us if we're calling it in the wrong kind of fashion. Too many arguments, wrong types of arguments. So we get some type safety here. And now if we actually call the function, we need to designate our mod unstable, because the FFI API is still unstable at this point. We also need to use allow FFI and allow read for the URL, I believe. And I have the mod wrong. Yeah. Wow. And we can see that actually calls some function which does apparently return 3 plus 5 equals 8.
So just can we look at libsession-1.so real quick?
We can, but it's not going to be pretty.
So is this just like the compiled down version of the lib.cpp?
Yeah, this is compiled down and compiled into or linked into a shared library. Yeah.
And what does that process look like? Going from lib.cpp to the SO file.
So I have here actually the build file done in Deno as well. I'm somehow inclined to use that.
Of course.
So I have here a couple of Deno commands. First, I used the Deno command API to call G++, the compiler, with a couple of flags. We need the PIC place in. Let me Google that.
Got it. Yeah, so this is a separate process to go. So before the FFI can even be called, it has to be called on the compiled version of the CPP file.
Yeah.
And not the raw CPP file.
Yeah.
And I think if people are familiar with C, that's probably expected. Right.
Yeah. Anyone who has ever done any native programming should know, compiled languages need to be compiled before you can use them.
Mm-hmm.
If you've only ever done JavaScript and scripting, for a scripting language, the engine will actually interpret and kind of compile your code as it's being run. But for native languages, you have a compiler that will do the compiling beforehand, and only after that is done, you can actually run it.
Yep, that makes sense.
Yeah, so we have a couple of build commands here. The position independent code is needed to do a shared library, and after we've built the session one, then we can link it into a shared library. Also done with Deno, just because it's nice.
Yeah, that's awesome. Cool. Yeah, so this function works.
Yeah, it works, and of course, it's not terribly useful. Like, I could do 3 plus 5 in JavaScript as well. Why do this? But foreign function interfaces give us some tools that either might not be already available in JavaScript, or would be kind of arduous to do. So, for instance, we have here in the libcpp double to bits and bits to double. So let's copy this double to bits. And here we have, it took a double parameter, so that's a 64-bit floating point number, and it returned a 64-bit integer. And the bits to double work the other way around. So it takes a 64-bit integer and returns a 64-bit floating point number. Now, I call our double to bits with some floating point number. What might happen? Run this.
Can I guess what happens?
Yeah.
I think it just returns, it removes everything beyond the decimal point, right?
No. This would be. It could go either way.
Let's find out. I'm curious.
What it does is it takes the kind of binary representation of the double value, so the floating point number, and it reinterprets that as a 64-bit integer. You could do the same in JavaScript using array buffers. You make an array buffer that you designate as floating point 64-bit array, and then you kind of reinterpret that array as a 64-bit integer array, and you would get the same result. But we get this in a few lines less, though need a build step and all that. And we can, of course, also check that if we do this kind of twice. So we take the double to bits, and then we call that with lib symbols. We call the bits to double with that result. We should get the same value that we passed originally. And it definitely looks the same. So we can interpret and reinterpret numbers kind of between their different styles using this. Still not terribly useful, but gives an idea that with foreign function interfaces, you get more kind of power from the very small amount of bits that you need to use.
Yeah, it definitely seems like your ability to manage things at the bit levels, it becomes easier, in C, which makes sense. But that's very cool.
Yeah. If we then want to do something actually useful, most of the time with a foreign function library, like you might be dealing with bits and numbers quite a bit. But in the end, you probably want to have some kind of data sharing going on. It might be just strings that you're sharing, which is already really, really complex at the very deep level. But often you might have a foreign function library that gives an API to create some kind of object or create some class instance that you then can use later to do any kinds of all kinds of interesting things. So in the libcpp file, we had this example class here, and it gives us exactly that. Gives us a class that can be used to do all kinds of interesting things that might be useful. So we see here that we have the lib example create function, and we see that it takes a const char pointer. This is C++ way of saying string, and in Deno FFI, this could be either a pointer or a buffer. The difference between a buffer and a pointer in Deno FFI is essentially that a buffer is owned by JavaScript, whereas a pointer is generally foreign function or foreign language owned. And this kind of only applies to outgoing data. So data that leaves JavaScript. But yeah, here with we want to give a const char array or const char pointer to the C API. We're going to use buffer, and the result here was a pointer. So we get the lib example pointer as a result. So we'll get a result pointer here. And now, if I call this, or try to call this, it says that the first parameter should be a buffer source or null. We don't want to give a null, which would be a null pointer. So we need to create a buffer source. A buffer source is usually a uint8 array. And the easiest way we can do that with Deno, or with actually this is just normal JavaScript, is that we create a text encoder. And now using this text encoder, we can encode strings into their buffer representation. So we get our string buffer using encoder encode, and it takes some input and returns the result as a uint8 array. Uint8 array is perfect. Deno FFI loves uint8 array over any other array, so always use uint8 arrays if you have the possibility. And now we just need to figure out what we're going to write in this buffer of ours. Let's write what the F is FFI. And as we're doing this kind of on our own, well, let's actually just do it like this first. Now we have a string buffer, and we put it there. Yeah. We can now run the code. Astute watchers will look at this code and think that's not quite right. But we get a pointer. We get a pointer integer. At the moment, Deno FFI deals with pointers as just integer numbers. Though this might change semi soon.
Mm-hmm.
But what can we do with this pointer? It seems kind of useless. Well, let's take a look at some of the other APIs we had here. We have here this libexample getCstring function. Let's take that and parameters for it. If we take a look at it, it takes the libexample as a pointer. So we say pointer. This is kind of because here we're getting a pointer. So when we're passing the class object kind of back out, or class instance back out, we still use a pointer. And as a result, we get a const char pointer. So yet another pointer here. Now, let's call that function. We'll call the result cstring. And we'll get cstring from our pointer. We get yet another pointer value here. So that's yet another pointer number, which is not quite useful yet. But now we know that this is a C string, and Deno offers a function for getting the string value out of a C string. There's this Deno unsafe pointer view and its static method getCstring. We can call it with a pointer. We don't need an offset here, but we can say we're not offsetting from the pointer, and it should return as a string. Now, if we console log that string, let's see what happens. Any guesses?
I think it's going to be WTF is FFI.
It should be, mostly. But it's actually an error. This is not valid UTF-8. If we try this again a couple of times, it might. No, it's not going to be valid UTF-8. What went wrong? Well, one thing we can try here is we get an array buffer out of this instead. Let's go byte length 24 bytes. That should be well enough to get us our string here. And now we can use the text decoder to decode this buffer of ours. It's still named string, but let's not care about that too much. And this will return us a string. Let's console log that, and it doesn't look quite correct.
It's a little wonky, yeah.
Yeah. So this is what happens when you don't do things quite the right way with foreign function interfaces. the error we made is that the C string needs to be null, needs to have a null at the end. There's no way for C or C++ to know when the string ends. So it expects there to be a null byte at the end of the string. And we didn't put in a null byte, so it just kept reading until it found some random other null byte later. And that's why we see this weird string here. Now,
interesting.
Now if we go back to the get C string version here, now we should see, oh, we're still not seeing it.
Not valid UTF-8.
Yeah, now we're going like badly off script because
all good.
Like this should have worked. I think. Now we're down to debugging. Ooh, Christ. Now I'm wondering, did I actually check this before?
In your GitHub repo, you have. Oh no, that's all right. Deno unsafe point of view dot get C string pointer. Yeah, you console log the pointer.
Damn, did I not actually check this beforehand? Yeah, I probably didn't actually try this. Now that I think about it. Well done. Yes. What about the length? If I take the length here, well, it's probably gonna fail just as nicely.
That seems like it worked.
That worked fine.
Yeah.
Yeah, that's like exactly correct. Oh, why? C string. Yeah. Okay. Oh.
There you go. Yeah, that's what you have in the repo.
Yeah. Maybe actually probably just now I probably didn't actually put the escape there.
Yep.
So
I think
actually up.
Yeah, I think maybe you were passing in some other parameter or something.
I was probably doing either this or this, like kind of mistakenly passing something else than 0. Okay, now we're back in business. Yes.
Yep,
yes.
we're back.
Yeah, let's pretend nothing ever happened and it's all fine.
Yep. Erase everything.
Yeah. Now if we call the get C string on this pointer that we get from the get C string function or the FFI API. Now we actually see our WTF is FFI.
Mm-hmm.
Everything works as expected. Yeah.
Yep.
It definitely wasn't a cut in the middle.
So all I have to do is add the null character at the end of the string, and then see
Yeah.
parse it properly.
Yeah. There are different ways different ways that C APIs, C++ APIs might work with strings. Actually, in the libcpp here, we're internally using the standard string function, the standard string class, which would also accept a way to build it with a non-C string character pointer and a length, in which case it would simply read as many bytes as you've told it to read, and it would believe that you're correct. But we were using the C string to kind of see this error in action.
Nice.
Often C APIs will just use C strings. That's kind of why they're called C strings in the first place. One thing we haven't been doing here is getting rid of our our excess, the instances that we've created. So here in the lib example create, we're creating a class instance on the C++ side, and we get a pointer to it. The pointer it's an address. It's kind of this particular instance's home address, but it's not the instance itself. And now here we get to the very interesting parts of doing FFI with JavaScript. This pointer, for JavaScript, it's just a number, or it could be just an object. But JavaScript doesn't actually understand that there is a C++ struct somewhere out there in the world that depends on this pointer. JavaScript will happily get rid of this pointer and leave that C++ object there where it was, and it will never ever get garbage collected. JavaScript does garbage collection. C++ normally doesn't. So we need to kind of plug or do the interfacing here. We need to be careful with what we create. We must also destroy. And that's going to be kind of our last bit here today. So in the libcpp, we have a couple of more APIs. We have the libexample delete and destructure. Let's take those and define them here. They both take a pointer and they return nothing, and that's void in common parlance. And we'll just define these. And now, if we this time go with first the correct answer, when we're done with our example instance here, we must call the delete function for it. It's just as easy as this. We just pass a pointer back to the foreign function library or foreign library, and tell it to get rid of this pointer. Nothing happens. Everything is fine. What actually happens is that the instance that we created, it is being deleted, which in C++ means that the memory behind this pointer is now released according to how the example class should be released. The example class doesn't actually have a destructor, so it uses the default destructor, which basically gets rid of this standard string here and all the data that this class has. So how can we be sure that it actually did something? Well, if we take here our getC string function, let's first call it like this, where we have the console logging going on. It still logs our correct correct WT is FFI string. But now if we call it again after the deletion, I have no idea what's going to happen, but it's going to be fun. Oh, segmentation fault. This is a use after free error. We deleted the instance here, but now we're trying to use it to call some of its methods. But the instance doesn't exist anymore. It's gone. You cannot use that which has been freed. So we get segmentation fault. In other cases, it might be something weirder that happens, but this time it was segmentation fault. So now we can be sure that we've properly released the memory that we created. Normally, you probably shouldn't try methods out after you've deleted. You should just trust that it has done the deletion.
Right.
Here we can try things out. There was also the other method that I defined, the destructure. And this is now the wrong answer, mostly. If we run it, nothing happens, everything works fine. And this might segmentation fault again as well. No, it doesn't. Yeah. So now we can actually, we think we've deleted or we've destructured the object, but it's still working fine. The answer is that this destructure function is calling the C++ destructor of the class. And the destructor of the class will, well, this goes a bit beyond my pay grade, but I think it's calling the destructor of the standard string. And the standard string in our case happens to be somehow optimized, or maybe it's, it's something wibbly wobbly timey-wimey.
Sure.
It is not actually, it doesn't need to release any memory. So it just does whatever it does. And the example class, its destructor has been called, but its memory isn't being released. It's not being deleted. So this memory that is allocated for this class instance is left alone. It can still be used, and as long as the methods that are being used don't cause seg faults through other memory issues, it will still work, i.e. we've actually created here a memory leak.
Got it.
This is not usually really kind of a thing you need to worry about, except if you're binding into an actual C++ API, then you really need to know which destructor you're calling. Here it's just kind of for show that, things can go wrong in many ways.
Yep. That's why this is the dark arts.
Yep.
Awesome. Yeah, that's all very interesting, and I think this is such a good intro into getting started with FFI, and just showing how we can start calling functions in C with TypeScript and JavaScript. So that's all really awesome.
Yeah. Hopefully we'll have more sessions like this, and we'll get to kind of dive deeper and see what are the things that we can actually do beyond just putting a string out into the world and getting it back.
Yep. Is there anything else on these sets of functions that you want to mention?
I think we've decisively covered all the ground we can get out of these ones. Yeah.
Okay, great. What should we expect in the next chapter, the next episode? What do you think? What are you thinking of?
Let me take a look at my my old notes.
Yeah, I mean, you don't have to answer it on air.
Yeah.
Cool.
So I'm hoping that the next session I could go more into kind of advanced concepts or advanced features that we can do with Deno FFI, dealing with more more intricate classes and finding more ways to cause seg faults. But also multi-threading would be a nice touch to just lightly look into. Deno FFI or JavaScript in general is single-threaded. So when you're working with JavaScript, you kind of expect that there is not going to be any threads involved. But with FFI, you can get threads even without JavaScript workers.
That's awesome.
And then the question becomes, how do you communicate with those threads in a safe way? Usually in native languages, you have channels passing messages between different threads, and Deno FFI essentially just does that for you. If you make a callback, or if you create a callback in Deno FFI and you pass it to a native language, that native language can safely call the callback from any thread, and it will not cause weird issues.
That's really cool. I mean,
unless
yeah, I think there's a lot of really fun applications for that multi-threading. With Deno. So yeah, really excited to dig into that in a future episode.
Yeah.
All right. Well, thank you so much. I'm going to end the recording, and